So it's really important to know what average is being reported in a study. Is it the mean, is it the median, or is it the mode? It really does make a difference. Now let's look at the shapes of a distribution, and we'll use words to describe the shape or the picture that that data gives us when it's plotted in a histogram or a line graph. So the words we'll use to describe some shapes might be symmetric, where the left half is a mirror image of the right half. We may use the word left skewed, where the data values are more spread out on the left side, which gives you a left tail. Distribution might be right skewed. The data values are more spread out on the right side, which means there's a right tail. We'll also use the word variation. That describes how widely the data values are spread out about the center of a distribution. And finally, we'll also refer to the number of peaks or modes. It's possible that your data set might have more than one mode. It might be bimodal. And the picture of that data would lend us to have two peaks. So if the data had three modes, we would see three peaks. If the data only has one mode, then there would only be one mode, one peak, and that's called unimodal. Okay, so just starting off with, let's say, working with the modes. I've got some examples here, and we want to describe the shape of the distribution and making sure that we mention how many peaks that it may have. So taking a look at heights of 1,000 randomly selected women. So we've got heights on the x-axis, number of women or frequency on the y-axis. And if I were to plot that data, what I would see is a curve, kind of like something you may have heard before, a bell-shaped curve. I would expect, since I'm dealing with one population of women, I would expect to see a nice symmetric curve. That just means the left half of the data is a mirror image of the right half. So this figure, this distribution would be symmetric, and it has one peak. And one peak just means it's unimodal. Unimodal. So, what if we looked at the next example? I've got some data, and it's the number of hours spent watching football on TV. And I interviewed or surveyed both males and females. So on my x-axis, it's the time watching TV. On the y-axis, it's the number of people. So, I mean, times might be 5 hours, 4 hours, 6 hours, whatever, but it would be numerical order, left to right. And come to find out that the women that were surveyed had a tendency to gather around this high spot, which is less than the number of hours men watch TV, which had a tendency to gather around this spot. So what I see here are two peaks, which means we have two modes. And when there are two modes, it's called bimodal. And these types of bimodal graphs will come about when your population sort of has two, well, actually, you have two populations you're working with, a population of men, which is different than a population of women with respect to, in this case, the number of hours that you spend watching football on TV. To me, it makes sense that the women, the mean for women, would be the number of hours that women watch football would certainly be less than the average for the number of men that watch football. So, two populations, men and women, have a tendency to lead us to two peaks, which are two modes, which makes that bimodal. What would the data look like for this situation? Weekly sales through the year at a retail clothing store for children. Okay, so they looked at weekly sales for an entire year, and what was noticed is, excuse me, let me just describe this. On the x-axis, we have the months, and on the y-axis, that vertical axis, we have the weekly sales volume. And notice that there's a peak around spring sales. Then the data kind of goes down April, May, June, but there's another peak around August, back to school sales. Then there's a lull and another peak around the holidays. So this data lends itself to have 3 peaks. So there are 3 modes. And that's because the sales have a tendency to spike during different times of the year. So we saw 3 spikes here. Another set of data. The number of people with a particular last digit, 0 through 9, in their Social Security number. So if I took a lot of people and I said, hey, what's the last digit of your Social Security number? Then that type of distribution would end up being flat. There would be no peak, no high points. It would just be a flat distribution. When you have a distribution like this, where in this case, every value has the same chance of being chosen as a last digit, this is called a uniform distribution. No peaks, just basically a flat line. So those are some examples of some shapes of distributions. With respect to maybe their peaks and a little bit on the symmetry. All right, so let's continue. Here's some examples of symmetry, skewness, and variation. So like the heights of women that we saw earlier, we saw that that one was symmetric. Nice bell shape, middle line of symmetry. Or it might look sort of like an upside down parabola. That one's symmetric. Left and right, if you folded it, they would be mirror images. And here's an interesting one with 3 peaks, but clearly it's symmetric because there is this middle point for which if you folded that distribution along that dotted line, the left side and the right side would be mirror images of each other. So those are some examples of symmetry. Here are some examples of skewness. So I've got a left skewed and I have a right skewed. And then I have a symmetric. And we're going to look at some qualities about these particular shapes. First, if your shape is left skewed, which means there's a tail here on the left, what usually happens is there are outliers to the left, low-valued outliers, that grab this distribution. Basically, it's like you're pinching the distribution and pulling it to the left because an outlier pulls that distribution in its direction. And what you notice is that the mean gets dragged right along with it. So it's not the best average to use to represent that population. So notice the mean is lower than the median and the mode. Now, if you took a graph and pinched it and pulled it out to the right, then you would see a right skewed graph, which means there's an outlier over here at the high values. Again, that outlier has a tendency to pull the mean towards it. So instead of the mean being in the middle, it's now skewed towards that outlier value. It's larger than the median and the mode. And just another one dealing with a distribution that is symmetric. What is really neat is when you have one of these single-peaked symmetric distributions, the mean, the median, and the mode are all equal to each other. very, very important for what we'll do later on in Chapter 6. So now if I took this symmetric shape and grabbed, let's say, the right end, if I pinched it and pulled it to the right, I would have a right skewed distribution, and that mean would follow towards that skewedness, towards that outlier. Same thing if I grabbed the left side right here, pinched it and pulled that shape left, I would have a left skewed graph, and the mean would have a tendency to follow towards that outlier. When you've got a skewed distribution, the median is going to be your better measure of the center of that distribution. Not the mean, because the mean is skewed towards that higher or lower value. So very important piece of information. When we have symmetry with a single peak, the mean, the median, and the mode are all equal to each other. Okay, last characteristic of a distribution that we want to cover is variation. Variation is the spread of the data about the center of that distribution. So the center here, I didn't do a really good job of drawing those. The center is where that peak occurs. So we can see we've got some symmetry and we have a center of that data. Again, that's where that peak occurs. So the question is, if you look at that peak and you look at the data on the left and the data on the right, how spread out is that data? So this first symmetric kind of bell-shaped distribution has a low variation because it's very thin. It's not wide. So the data is closely centered around that mean, median, and mode. Here in the middle, a little further out from the center, so it would have a moderate variation. And then the one that's furthest right, the data is farthest, with respect to the other two, the data is spread out farther from the center value than it is in the other. So it's kind of with respect to each other. First one is low variation because it's a pretty skinny symmetric graph. The next one's a little wider, and the third one is even wider. So that's another way that we can describe the distribution. Didn't mean to do that. Okay, let's look at this situation. How would you expect the symmetry and variation to differ between the times in the Olympic marathon and the times in the New York marathon? So think about the runners. Olympic runners. Those guys are professional runners, and to make it to the Olympics, you have to have a pretty decent running time. World record times, actually. So for Olympic runners, I would expect that data, which are basically their running times, to have a very small variation. Not very spread out. Now, with respect to the New York marathon, we have runners, heck, of all skills. Therefore, the variation would be much greater in the New York marathon. We have males, females. We have those that run probably professionally, but those that just do it as a hobby. So we would have a much larger variation or spread in those running times. Okay, so here's a situation. I've got a graph, and all of these are nice symmetric single-peaked graphs. There are 4 of them on this display. The question is, which one has the most variation, which one has the least? So let's just label these. I've got graphs A, B, C, and D. Looking at these graphs, which one has the most variation? D, because it's much more spread out. Which one would come next that would have a smaller variation than D? So let's put these in order. D has the most. I would say C would come next. Then I would say A would be next, and B to me would have the least variation. And remember, variation is spread. D has the most spread, B has the least spread, and then C and A come in between that. So in my math lab, you can now go and work on the homework for section 6A. To wrap this up, here is what I've got, and I want you to do this on your own, then put the video back on to check your results. I've got 1, 2, 3, 4, 5. I've got 5 descriptions that I want you to match with 5 graphs on these last 2 pages. And these graphs, in these 5 graphs, one of them represents the weights of 3-year-old boys. One of them represents the chances of when you roll a die that you get a 1 or a 2 or a 3 or a 4 or a 5 or a 6. Chances of getting one of those numbers when you roll a die. Another graph represents the life expectancy here in the U.S. Another graph represents age at first marriage. And there's a 5th graph, one of those 5 listed below, that represents the body mass of males and females. So what I want you to do is, based on our talk above, take these descriptions and find out which particular distribution they go to with the 5 graphs that are given below. Okay, so let's wrap it up. Notice this first graph has 6 bars, and each one of those bars has the exact same height. So this would be a uniform distribution, and this one would be the distribution I would choose for B, which says rolling a die and obtaining a 1, 2, 3, 4, 5, or 6. The chances of getting a 1 when you roll a die are the same as getting a 2, a 3, and so on. So this would be a uniform distribution. There would be no peaks. Let's check out the next picture, the next graphic. Okay, so we see this bar graph. You can draw a nice smooth curve over it. Actually, that's already been done, so I'll erase my blue one. Given that smooth curve, we see a large portion of that data occurs between 80 and 95. So I would pick the life expectancy situation, life expectancy in the U.S., because there's a high percentage of the data that occurs around or between like 80 and 95, and that is the life expectancy here in the U.S. Most people live to be between 80 and 95 years old, or 80 and 90. So that peak occurs around that most common life expectancy. Okay, here was a nice picture, a nice symmetric curve. And I would choose the weights of 3-year-old boys for this particular curve because it's symmetric, and this is a phenomenon that occurs. If I take one single population like 3-year-old boys and I determine their weights, then we will end up with a symmetric graph. If I did the weights of 3-year-old girls, I would have a nice symmetric graph. If I did the heights of women, I will get a nice symmetric graph with one peak. The heights of men, symmetric graph with one peak. But if I put men and women together, then I'm going to see 2 peaks, which happens in this next graph. I see a graph that has 2 peaks, which tells me this came from 2 distinct populations. One peak represents one population, the other peak represents the other population. So I would have chose the body mass for males and females for this graph because I see the 2 peaks. I think males may have a higher body mass, so the males would cluster around this larger value on the scale, and the females would be around the smaller body mass value on that scale. So two populations, male and female, will give me two peaks. And then this, this last picture. I've got some data. If I drew a nice smooth curve over it, I would see that it looks kind of right skewed. There's a peak here that's occurring like between maybe 18 and 30, where a large amount of my data occurs. And, well, the only last one to pick is the age at first marriage. So this would match with D, because just think about it. Age at first marriage. I would expect there to be a large majority of my data around, in this case, like the 18 to 30-year-old category. Now, there are some outliers, so this one is actually skewed to the right, because, I mean, it's possible that some people's age at first marriage is much higher than 30, like we have some in the 50, 55, and 60-year-old categories, ages at first marriage. So this one is skewed to the right because there is a tail on the right, but the majority occurs between or where we see those higher peaks. Okay, so that's it for 6A. Go to my math lab and do the homework.